thank Bob for the introduction. I'm involved in the NNSA as the CDAC deputy director. CDAC is one of the center at Carnegie Institution doing the mainly try to outreach the energy, the NNSA application with static pressure. Here I'm talking another center also at Carnegie that is called the Energy Frontier Research Center under extreme environment. So it's EFREE, E3. This is one of the broader center in terms of trying to solve the energy problem. So let's see. The talk, this one has a laser pointer. Okay. The talk will first I will introduce what is the DOE EFRC and the Energy Frontier Research Center and Extreme Environment. And then our extreme environment is not quite as extreme as the last talk, which goes in MEV. We are mostly talking about EV range. For some chemical energy and sometimes the nuclear materials, but it's more studied, the different nuclear material, and but not the actual nuclear property. But this is a very rich field, and you can see that this in the last couple of years. Here I'm giving some example here. I don't expect you followed any of this in detail, and I won't be able to have the time to discuss any of it in detail. But this is more of giving the impact of extreme environment in terms of what we can reach with static pressure. Let's say nominally 3 megabar or 300 GPa and several thousand degrees, up to EV range, up to like 10,000 degrees. And in this region, every pressure temperature region, you can think of this as a totally new blank field. And whatever property you know at ambient condition, when you put that in that condition, will be extremely different. Just about, we're still studying the element. For instance, if you pick any element, like sodium or lithium, you would think that before you do the study, you think that it's a very boring element. It's just close-packed free electron metal. But when you start doing that, you find that more than 10 different structure, and it has many weird physical chemical properties. That's what we're trying to use there to solve the energy challenge. I just used this picture to show that because you probably heard many of the people talking about that energy in the future, and with the way we consume energy, with the way the environment is going, and it's not sustainable. If we continue this way, even with the progress we have in science, it's not sustainable. So at some point we're going to hit a granite wall, or sometimes that will be a real disaster, unless we have some way to solve the problem. So DOE does have this vision, and so they started this thing called Energy Frontier Research Center 2 years ago. These are actually small centers, like $3 million a year, 5 million center. There are 46 of them, and explore many different directions. And in the past, most of the DOE is multi-billion dollars funding agency, and I understand that a couple of days ago you heard about this science policy and so on. But most of DOE support in the past was for more applied, and this center is really for harness the most basic and advanced discovery. So just think like, okay, now, just like if you look 20th century, if you think what are the most important discovery in the 20th century, and most of this, they are not really, you could plan ahead of time. So you just go with the most basic discovery and see how this can push the energy science forward. So again, this I don't expect you to see the fine word here, but basically the DOE basic energy research, they have different level of from most basic, that's called grand challenge, and discovery and the use inspired basic research. So this still consider how you use it. And then applied research and technology maturation and development. So the EFRC actually covered this range, and the other ones are the DOE, so they call core program, so the existing program. And the EFRI, the Energy Frontier Research and the Extreme Environment, our center is dealing with the most basic part. And the bottom are those workshops that DOE in the last 10 years, they work out many workshops. And those workshops defines how do you, for instance, how do you handle the hydrogen energy, how do you handle the superconductivity, this is hydrogen, and nuclear energy, electrical energy. So this is a very broad spectrum problem you need to solve. And all those are related to energy, to energy and the materials. So we start from the basic materials approach and to see what fundamental discovery we can do in the materials side, and it has a major impact here. So for high pressure, the high pressure, although you may see many papers on high pressure, but how many of them? I mean, they are in physics journal, it probably say a couple %. But how many of high pressure phenomena exist? It's probably 10 times everything we know currently at ambient pressure. So in that ratio, it is nearly unexplored, and just about every material is studied to the pressure temperature range, like 3 megabar and 10,000 degree. Conservatively, you can say that you can discover 10 times more of what you know at ambient pressure and temperature. So just the material base are much larger, but you cannot just blindly study that. It just will be lost in that. So you need to have some guidance. So we actually, after there's some novel physics and chemistry in the extreme environment. Just like at the beginning of the 20th century, people just explored the low temperature and found the superconductivity. And if without the exploration of low temperature, that time probably think that's totally useless, you would not possibly be finding that. The BCS theory is very unlikely to come out of blue. So this is because you have two ingredients. First, you need to go to low temperature. Second, you need to be able to measure the conductivity and the magnetic susceptibility, so you know it's a superconductivity. And then you see it's new phenomena. So our goal is also the same way, to explore this high pressure region with some plan and logic. Later I'm going to give a lot of examples. It looks like they are not connected, but actually they are. But I don't have time to go into that detail. Then, because we already know there are some extremely favorable property at high pressure. For instance, at high pressure you can find the densest hydrogen. You can find the highest temperature superconductor, higher than what you can have at ambient condition. You can find the hardest material, the most resistant material for, say, like if you want to build a nuclear power plant, if you want some way to avoid say disaster, there's materials you can most resistant, and the best thermal conductor, the best thermal electrical material. So you have a lot of example, but for energy application, you need to be able to either bring the material to ambient condition, or you have some way to understand the basic principle so you can make something similar to that, or learn from that to synthesize or to design some materials. So that's a general view of this center. And our approach is we build, in this center, we have a theory group or theory collaborators. And we use the synchrotron a lot because synchrotron is very well coupled right now with the static compression with a very small sample and with a very intense beam. By the way, the synchrotron usually run at GeV range, so that's higher than what we talk about MeV. But the X-ray come out is usually KeV range. And we use a neutron source at SNS, also used to probe high pressure sample. And we develop different high pressure equipment and electromagnetic probe, and use this to study the material in the extreme environment. This is a part of sample chamber taking out of diamond cell. I understand yesterday that Crystal Katali have given a talk. She probably mentioned a diamond envelope cell, so I'm not going to talk any more on this. But this, although the diamond envelope cell can reach very high pressure, then half the material, once you release the pressure, it will go back to ambient condition. But there are also quite a few, and they are, I would say maybe like 20-30% materials you can actually go to high pressure temperature and then keep it that way and bring it back to ambient condition. So the one important part is that we want to see whether we can recover and those materials for the important energy applications. Okay. So this center, we have a rather big teamwork, including all the different parts, and we have a very, very large number of new technology we can use. And in the past, the high pressure is used mostly small science in university, like yesterday example in MIT. There's one professor and several students working on specific problem on earth science. That certainly is very important. And on the other hand, if you really want to explore a very big field, you need to have all the tools in hand, and you need to have all the talent in hand. And so we're not limited by, and we also have collaboration, so we're not limited by any of this existing what we have. Okay, so for the hyper technique, we are developing low temperature diamond cell. We develop different kind of cell with different opening, and for neutron, for synchrotron, and each one optimized for different part. We also even grow our own diamond because the natural diamond is not quite good enough, and so we have a CVD method. We can grow our own diamond, make it bigger and purer, and also have better impurity property that it can work better with as an envelope. Also, we use the new neutron source, the splitting neutron source at Oak Ridge. We use the synchrotron source. The synchrotron is currently about more than half of our activity is there, because the synchrotron X-ray already developed like many different special methods to study almost the whole textbook of solid state physics, from structure to electron property, phonon property, the ferroelectric property. So all those you have some synchrotron probe developed. But also at ambient condition, you have you can study nanoscience or some of those properties by vacuum technology like TEM, SEM, or ion beam, and so on. At high pressure, you have to reach the sample under in a high pressure environment. So you have to have a very penetrating beam. So it's either neutron or X-ray. So X-ray synchrotron is a major tool what we can use, and we have a beamline. This one supported by NNSA. It's called HPCAT, High Pressure Consortium Collaborative Access Team. That's the name of this special beamline. But also we have access to many other beamlines. The reason you need to access that is that there are some beamlines they designed especially to push the frontier. For instance, the highest energy resolution. Now they can get 1 millieV. this is also MeV, but a small m, energy resolution. And some of this can get very high energy X-ray, that in this case is several hundred keV. Some of this has a better way of doing very small spot, like they can get to 10 nanometer resolution. So in that case, we cannot build everything in one sector, because then you make it too complicated and you cannot do anything well. So here most of the study we use this beamline for the most routine study, but for special study you use all the different beamline at the single time. So this also is a program supported by CDAC and NNSA called HP Sync. This is to reach out for all that. Okay, here now I'm giving some example quickly. Here I want to emphasize now for synchrotron X-ray, 200 nanometer became routine. In the past, we used most of synchrotron beamline in the world. We use micron size. Why you need smaller size? Because if you want to get a higher pressure, one way to do it is to have a much smaller tip. And so because force per unit area is pressure, if you either have a smaller area, you have more force. And so once you get a smaller area, that's a way you can preserve this sample environment and pressure higher. So far, we haven't reached much higher than 30 GPa, 300 GPa. But now with the 200 nanometer beam, we will be able to really fine-tune the sample area. We can distinguish the. Also, once you get to this pressure, how do you know you're at that pressure? You should be able to probe the sample property. For instance, you probe the density, and that's one thing that use shockwave, you can measure pressure density relation. So with 200 nanometer beam, you can start to see the different area to probe the different sample, and also with the emission spectroscopy, you can do it chemistry there, and you can measure the pressure. Another very interesting application is that in the past, at high pressure, you can only do polycrystalline diffraction, and single crystal X-ray diffraction give you a much better result. But if you have a sample and high pressure, it will be crushed. You can re-synthesize the sample at a high pressure, but usually you only get a micron size. And in this case, you can pick a small crystal and do a micron size single crystal diffraction. And for instance, why do you need to have a single crystal diffraction? For instance, like this is I said, sodium became very complicated phase diagram. It has some structure with up to 120 atom per unit cell, and so all those have complicated crystal structure. But how do you resolve that? You need single crystal diffraction. Otherwise, with the powder, you get thousands of lines. You never resolve that. And another one is the SiH4. It turned out to be a superconductor at 200 GPa, but the crystal structure again is if you have powder only, you cannot quite resolve it. Okay, so this example, SiH4 is a new approach to try to get metallic hydrogen, which is one of the holy grail in high pressure research, trying to make hydrogen into metallic phase. Hydrogen, you know, at ambient condition is a gas. Compress it, became solid, but it is van der Waals solid like helium, because hydrogen you have two atoms form a molecule, and the electron structure is just like helium. But if you have increased enough pressure, hydrogen will become a metal, and that's shown in very high temperature, near the plasma state. But at ambient condition, if you can put hydrogen become a metal, it has many really weird structure and property. For instance, will become one prediction is become a room temperature superconductor. Another prediction is become a very fluid and a much better fluid than lithium. Lithium battery is one of the major applications, but not everyone pushing in any application. But if you can get some proton conductivity from hydrogen, that would be really great. Also, it's related to fusion field and related to many other things. So that's why it became a sort of a holy grail, but we never reached the pressure we can make metallic hydrogen. So one suggestion by Neil Ashcroft is, how about you make a hydrogen-rich material? You have a lot of hydrogen, just dope something and compress it. Maybe that you can make impure metallic hydrogen. So this was one attempt of that. Okay, now there are a lot more attempts of calculating a doped metallic hydrogen. In this case, it's this Si2H6 and predicted to be a high TC, high temperature superconductor at 134 Kelvin. This has not been synthesized. This was only calculation. And this one was synthesized. This one has more hydrogen than any other known compound. We made a xenon hydrogen compound, but the relation is still van der Waals compound. So even when compared to 200 GPa, this did not become a metallic. So that's again, it didn't quite work out as we hoped. So when you explore this extreme, you quite often you see something really interesting. For instance, normally you think xenon is a inert gas; it does not react. But actually, at high pressure, you form many different van der Waals compounds with hydrogen and others, and others. So understanding that is quite interesting. And this is another example of the xenon compound. Okay, now let's back to something we know is a superconductor. For instance, the calcium metal is at the ambient condition is not superconductor at all. It's just a regular metal. But at high pressure, it became a superconductor. Not only that, it became a highest temperature superconductor. At the ambient condition, the highest temperature superconductor for element is 10 Kelvin, and the calcium reached 26 Kelvin. So it's interesting to know why that happened. And so first thing we do is to understand what is crystal structure. Calcium also has a very strange series of transition. It goes from, usually at high pressure, you expect material goes from close to close packing. And so if you have BCC, body center cubic, and if you transform to FCC or HVP, that's closer packing. But this is completely reverse. You start with FCC, at high pressure it becomes BCC, and at even higher pressure it becomes simple cubic. Simple cubic has 6 coordination, BCC had 8, and the FCC had 12. So it completely reversed. And also simple cubic is, you can imagine that you stuck a ball on top of a ball. It's really unstable normally. So there were a lot of theoretical calculation, and no one could figure out why it's simple cubic. But it diffraction looks just like simple cubic. And we don't have a large single crystal, so we have a very small single crystal using the nano probe to determine the structure. Actually, it was not single crystal. It turned out to be rhombohedral distorted phase. It expands some, but not all that. But at higher pressure, it has even more transition. So the simple cubic is just like this, and then the actual rhombohedral is like this. But at low temperature, it has another structure. It's a rhombic structure. Okay, let's look at another simple metal. Back to sodium and lithium. As you said, the sodium has several phase transition. But how about lithium? Lithium is smaller than sodium. Actually, it has the same structure transition as sodium, and you can see that in almost the same pressure, same volume range, they have the same structure, like a BCC here, FCC here, and they all go become C16. So we determine the phase diagram of lithium. You can see it's very complicated, and also it turned out to be a room temperature liquid at 40 GPa. So at high pressure, this lithium is the lowest melting temperature of any known material right now. And also, lithium is very diffusive, and it's very mobile. So that's one of the use. Like there's a whole DOE program devoted to study lithium battery and the way of lithium moving in different compounds. And the reason we cannot really go higher is because lithium just goes right through the diamond. Okay, and now we talk about what known for the oxide superconductor. Now this is still the highest TC superconductor, but the way you can improve the oxide superconductor is by changing the oxygen deficiency. That's called doping. And usually you can reach, by changing the oxygen deficiency, you can have underdope, overdope, and then in between you have alternate dope. So that's the one you usually have highest TC. But if you do chemically, you can only put oxygen or take out oxygen. If you do high pressure, you can compress a different layer of oxygen differently, because when you're under pressure, they respond to pressure differently. And then you can actually have pressure also have a similar effect, optimize it and overdope it for one layer, but then the second layer taking on, and so you become the second layer is still underdoped, so you can have a second maximum that can push the superconductivity much higher. So this would be a way to design an oxide superconductor to make it higher. Let's switch gear to go to another extreme material, helium. Helium has the widest gap, electronic band gap, and so in the past, you could really never reach the helium at high pressure to study it, because the diamond band gap is 5 EV and helium band gap is 26 EV. And above diamond band gap, diamond absorbs everything, so you cannot get an optical spectroscopy of helium that way. And helium also in this region has many excitons. The exciton again here is a low energy exciton, has been widely used also for energy application. In fact, there are 2 centers of a 46 center dealing with exciton. One of them is just called excitonic center. But with X-ray, and this is related to development of X-ray technique, we can use inelastic scattering. This is equivalent to energy loss technique of electron microscopy. We can not only study the helium band edge gap and also the exciton dispersion as a function of momentum, and so we can get the whole picture of excitonic structure of helium. Okay, let me just move faster on some other subject. Also at synchrotron, we developed a nano beam technique to analyze the sample, the growth of several nanoparticles on the gallium arsenide substrate. This again is something used broadly for energy application, and with the synchrotron, with the nano beam, you can start to see all the detailed feature of this. And okay, there's more nano studies. Okay, now let's just move to one of the most recent study that we particularly interested. This is with the 4F metal, cerium. That it's also something cerium is the 4F electron is interested for the NNSA project for the next row, but for the 5F, but 4F delocalization is quite useful as a parallel or the model for what happened to 5F. This initially we studied the cerium aluminum metallic glass. metallic glass is a relatively new material, which is very useful for structure because it, unlike the metal, regular metal has because of crystalline, it has a cleavage, and it has a property which is will break at some crystal boundary. As a glass, it does not have a boundary, so it's all continuous, and so it has this better mechanical property in some sense, and so it recently has been well developed. That in the past it was difficult to make such a thing, but now with a very fast quenching, you can make films or even box sample of metallic glass. So here we're studying some of what happened to the metallic glass at high pressure, and the serum aluminum, because this tool has a very large difference in radii. Serum is almost twice as big as aluminum in atomic volume. So if you put it together, they do not form alloy. And there's a 100-year-old Russell rule that requires two elements form alloy. Their radii has to be within 15%, and the electronegativity has to be within this, say, plus minus this range. So aluminum and cerium is far separate. They only form intermetallic compound, which is a structure compound with cerium at a certain point and aluminum at another point, rather than alloy. That means totally random glass. But by putting them together and quench it, it forms a glass, and that glass is actually a random alloy of cerium and aluminum. So that was published a couple of years ago. And the reason is because by increasing pressure, the cerium 4F electron became delocalized, and then this is like an alpha to epsilon to gamma cerium transition. So cerium volume suddenly collapse. Once it collapses, it moves into the region of possible to have the alloy. So both the electronegativity and the volume collapse, and so it moves inside and form alloy. Okay, so this is another study using the synchrotron technique to look the 4F electron delocalization change from this to this. Okay, looking at the cerium LH. But most recently, last month, we found that it's not only it became the glass became a crystal, it became a single crystal. So every part of the cerium glass, it has the same orientation relative to the original way you spin that film. So the diffraction gives you a single crystal spot. You can take it out, and it is really a single crystal. So this was very puzzling, and this relates to a century-old question. Does glass has long-range order? I mean, the definition of glass, if you look on web, it says it has no long-range order. But if it has no long-range order, how can you tell if you have a long ribbon, this point and this point, they have same orientation once it crystallizes? I still have 5 minutes? Yeah, okay. So one thinking is, okay, maybe the crystal grow from one point to the other, but we cut two pieces of this ribbon and end up with the same crystal orientation, and so they cannot see each other. And maybe the glass originally has nanocrystal in there, so we did a high resolution TEM and look at all the X-ray diffraction and the electron diffraction, and in all this, you really don't see any crystal in there. So there's no way this has a nanocrystalline. It's not started with nanocrystal and just grow. Okay, so the final conclusion, it is a long-range topological order. It's not a long-range spatial order. Like the difference of glass and the crystal. Crystal has a long-range spatial order, so you can do diffraction. You can see it with the X-ray diffraction, neutron diffraction, or electron diffraction. You can see the direct peaks. But if you have only on long-range orientation order, that means that, for instance, this is demonstrated with, say, if a skydiver, they all have their hand hold to each other, but this is a real material, so you publish in the paper. But if you can, if you just arrange like this way very regularly, then of course you get diffraction. But if your hand can stretch, your ankle can bend, and you can get to a point that you don't see that order anymore. There's no spatial order, but still the connection is there. So that's called topological long-range order. And for the open structure glass, it's easier to see that. But okay, I don't have that picture. But if you feel, if it is really topological order, you have all the whole field close packed like the metallic glass. Then you visually you cannot see it, but with the computer simulation, we do see that change, and that was published last month. Okay, there's some more examples that we can make super hard materials, like also with nanostructure. This is what we found that using mesoporous diamond, carbon, and at high pressure, you can convert into mesoporous diamond. The hole will not collapse, and so you can make many high pressure many material like the super hard material, and preserve the nano microstructure. And this is another example of silica. Okay, so let me just conclude that this way is our goal is to discover at high pressure and recover for application. In fact, let's have several examples, like mesoporous diamond, mesoporous stishovite, and the thin aluminum glass. All those are recoverable. When you release the pressure, it will still stay there. It will not convert. At the high pressure phase can be recovered. And then we have a focus on the energy resolution and energy in the future. So this is, we just in 2 years, and the 2 years we spent a lot of time develop technique, but I hope that in 5 years we can really have some major scientific breakthrough. Thank you very much.